So just to make sure you're not scared, it might eventually kill all your bugs, but we're definitely not there. That's why it's called field report on a zero-day machine and not a zero-day machine. But you know, maybe in a few years. Actually, this is a topic that I've been dealing with for quite a while. What you see here on the first slide is a note from 2008. It's called the master plan. So I will not show you the whole piece of paper because there are a lot of embarrassing things on there. But one of the embarrassing things, definitely this line here, and I want to show it to you. It says, become an O-Day machine and build one. Okay, so that was 2008, and yeah, this journey is, well, now it's 2018, so I've been on this journey for the last 10 years, and today we want to give you an update on where we are with that. Now, before you start calling me a fraud, you know, let's just point it out in the first line. Of course, universal discovery method cannot exist for vulnerabilities, so you can't just build this machine which will just take code and arbitrary code and just tell you, okay, these are all the vulnerabilities and all the rest is good. But you know, that's kind of the computer science way of looking at it, and if you look at it more from an engineering perspective, then you'll ask yourself, okay, but what can we do? And let's be honest here, I mean, most of the bugs we see are actually not super complex things that we've never seen before. We're dealing a lot with, you know, the same kind of patterns of injection over and over again. And for these kinds of things, it is worth asking, how much of this can we automate? Now, what's the current state of things? I think that it will always be the case that finding vulnerabilities requires a very deep understanding of the code base that you're looking at, and you will all know the main strategy that is always a big part of doing this is just staring at the code for a very, very long time. And mostly this talk is about making that time you know, less. And now if we look at the tooling, well, I guess fuzzing is there, and a lot of the bugs that you don't discover are due to the fact that people are doing software testing. Guess that's not that, you know, it's not that interesting to hear, but that is actually a method that's really important for bug finding today. And then you see a bit of taint analysis and symbolic and concolic execution. I think there's also going to be a talk tomorrow about concolic execution coupled with fuzzing, and so you'll learn about that, more about that there. And so when I initially started off, I thought, okay, so there's so much research out there. Let's just take this stuff and then just put it together, and there's going to be your machine. And if you look into academia, you'll see all sorts of really cool things like theorem proving, model checking, dynamic taint tracking, grammar-based fuzzing, white box fuzzing, static data flow analysis, which we will talk about today a lot, symbolic execution, concolic execution I just mentioned, SMT solving for input crafting. I think there's also a training, and there's going to be a training at the end again where you learn a bit more about that. And even automatic exploit generation. So if you ask some academics, you know, what we're doing here is really pretty pointless because you could have just generated the exploit, you know. All right, but let's look into practice. I mean, for real. What do we see? We see fuzzers. People use fuzzers. That's the automation that we use. And we don't do that in a dumb way. I mean, you do see fuzzers that try to increase code coverage, and they will use some form of static analysis as well. We don't just look for crashes. We have runtime memory detectors that will tell us, hey, you know, you just wrote something past the end of your buffer. This would not lead to a crash right now, but I'm just telling you. And then there's static analysis, or looking at the code. And let's be honest, we are mostly stuck in disassemblers and IDEs, and we use grep a lot. Yeah, and I guess, you know, that's not really too advanced. So there's a bit that we can do there. Symbolic execution is used. I mean, you'll hear a lot that symbolic execution simply does not scale. That's true, but specifically if you look at, so for finding vulnerabilities, but specifically if you look at crafting of exploits, if you already have a crash and you just want to know what are the conditions so that I can actually exploit this, then symbolic execution is definitely something that people are using today, and that works. And still, I mean, if you compare that list of things that we have to what's on this slide, there's this huge gap between what research has to offer and what we do in practice. And that's especially true for static analysis, and that's something that we want to change. So I guess one of the big questions for me was always, why is fuzzing something that works so well? And I think the main reason is that fuzzing is one of the few tools that actually integrates into our workflow. And you're also coupling, you're combining two things here. One, the ability of the machine to just explore code really fast. And the other is you're actually telling it something, which is, hey, if I point my fuzzer to this interface here, then this is going to be an interface where I can get attacker-controlled data into the application. Now think of your classic static analysis report. It will tell you about all sorts of things that might go wrong, but the first thing you'll say is, hey, this is not attacker-controlled. This code is dead, something like that. And with the fuzzer, that code is definitely not dead. It is attacker-controlled because you selected that interface as something that you can talk to. And you're also saying something else. If this thing falls over, then that's actually a policy violation, meaning that's actually something that's security critical. And for static analysis, that's usually not the case. So here, the tool kind of benefits from what the analyst knows, and the analyst benefits from how fast the tool can simply explore these things. And I think Sean Heelan put this pretty well in his paper called Think Cyborg, Not Robot, where he said for static analysis this is not the case. So what he says is significant under-investigated potential exists for static analysis techniques designed for integration into a human code auditor's workflow. A human expert will typically have significant amounts of internalized knowledge, and integrating it with algorithms is non-trivial. So in other words, what we want to focus on is actually how do we take that knowledge that an analyst has and actually make perfect use of the machine to leverage that knowledge to find bugs fast. And so one of the first things I did there was, that was in 2012, an extreme form of leveraging analyst knowledge is to say, hey, just give me a bug, show me what that looks like in completion, and then, you know, go ahead, machine, and just find something that looks just like that or similar to that. So this is something that, that I call vulnerability extrapolation. It works, it's just that it's very expensive because you're saying, you know, you can only use it if you give me a complete example of a bug, and then maybe there's something like that again. Many times there isn't. So especially if you have bugs that are kind of unique, that doesn't give you much. So I then started looking at all different kinds of ways in which code is represented, simply to see what kind of patterns I would be able to formulate, and essentially started with a syntax tree that just decomposes the code into its language elements. Then at some point I wanted to model the control flow. So like you know from IDA Pro, your control flow graph that tells you this is how you get from one statement to the other. And then finally, and this is something very important for modeling vulnerabilities, data flow. So data flow meaning there's something I control, I want to know where it goes, and I want to know if there are any kinds of checks on that. And so eventually I needed to store that data, and initially it just went into these large pickled objects, and that absolutely didn't scale. So I needed a way to do it better, and I essentially I'll put that into a graph database and then noticed, oh wow, you know, all of these data structures, they're essentially describing the same code, so why not just put that together, and suddenly you can describe walks in that path that actually look at syntax, control flow, and data flow. And that's something that was a lot more powerful than that work in 2012, and essentially led to the creation of a tool that's open source and that you might have heard of before, because you know, I tend to give the same talks a lot of times. And so the tool is called Yearn, after the person who carries the master plan in his wallet. And it is essentially a search engine for vulnerability discovery. And it uses a so-called fuzzy parser, meaning you can throw things at it that kind of look like C, and it will do the best that it can to create these data structures of it that you can then search. And then there's a query language, and this is an extensible query language. You can kind of build your own abstractions to then use that as a search engine. And you'll see this today, so Niko is going to demo something like that today. But now let's finally come to the machine that we actually want to build, because this is the stuff that's behind it, and you know, this is my wild imagination of how that should look like. So on the right, you see a code hose. So it's essentially code dripping into the machine at high speed, so not dripping really. And then you see pre-calculated intermediate representations for the world's libs and frameworks. So it's kind of like these graph structures, and they're down there, and when the code comes in, you can check its dependencies, you can load these intermediate graph representations, and it will create a new graph representation for that code that flows in. And then on the left, is it the left for you? Yes, it's the left for you as well. On the left, you have the world's collective knowledge about vulnerability discovery. And our ODE Vollautomat is going to use this world's collective knowledge about vulnerability discovery and the intermediate representation of the code to essentially find all the toxic assets of the world's code, which you see up there. And then there are these crazy nerds, and they can do two things. One is they can actually query this machine and ask questions, as was already the case with that search engine approach. They can also add to the world's collective knowledge about vulnerability discovery. And one thing I didn't put into here, because it's just lots of errors, is of course they can also comment on what the machine produced, saying, hey, this is really not true. And that information will then go back into this collective knowledge about vulnerability discovery. All right, and so we now have a company, or I am part of a company now, and they're building this. And I think one of the big things I learned this year, I mean, it's kind of clear, you always know it, but no, seriously, it is a huge step from a research prototype to something that actually works if you throw arbitrary code at it and doesn't just crash and burn. And today we want to talk a lot about what we learned in that first year. So here are the core questions and challenges that we dealt with this year. One is language neutrality. We wanted to build something from the start that is actually capable of eventually handling arbitrary languages. The second is, it's pretty hard to distinguish between the input of the machine and the actual algorithm, but only if we separate this nicely do we get something that's generic enough. And finally, how do we build a big knowledge base? Because just taking lots of queries and storing them works for up to 10 queries. After that, it gets really messy. So looking at language neutrality, the first thing you might think is, hey, let's just use an intermediate language, just like LLVM would do. Intermediate languages are nice. They come in a form that's easy to analyze, so they have certain properties, SSA form 3 address code. And that's what we tried first, but it didn't really work too well. And the reason for that is that you end up at a lower level of abstraction than the actual source code. So something that might be pretty easy to analyze in that particular language, because the expression can be written as essentially one line of code, becomes very, very clumsy when you actually start rolling it out and compiling it down. There was another project in 2015-16 that I was working on where we tried to just do all of this stuff on binary. Kind of works, but it's very clumsy. All of the you start reasoning about memory accesses instead of the actual logic of the code, and that's where your language gets very clumsy. But there's another approach, and you actually just need to look back, travel back into the 70s, and if you dig long enough, you'll find a solution here. And it's called the functional approach for data flow analysis, and it's a very simple idea. Just don't care about the language too much. Just say that there are these instructions or statements, whatever you want to call them, and they are defined by a function. and that function takes some input and maps it to an output, and yeah, they're all connected through that graph, so you get a system of equations essentially. Solve them, you're done. That's the idea. And if you look at that in practice, so here's a bit of code that shows this. So you have this code where you're reading something from getHeader, you're then checking it against null, it then taints this thing called command and then goes to exec. So what you now do is you attach the facts to each of the nodes. So here at getHeader you can say, okay, X comes from the network, so X is tainted. And then you simply propagate this through the graph, and each of these nodes here is just represented by a function. And so here's an example of that. The one that really matters in this example is just the plus. The plus takes something that's tainted, which is the X, and it then means that the return value of this is tainted. So you can say the transfer function of a plus is if you get X and Y, then if X or Y are tainted, then the return value is tainted. And then you can imagine each of those has one, and then you start propagating this taint, and eventually you reach this fixed point, and you can say, okay, now I have my statements at every node, and here I can see I'm calling exec, and by the way, CMD is tainted. That's essentially how taint analysis works. And now there's one great idea then, a few years into the future from the 70s, which is in 95. People say, hey, don't take out those transfer functions and just represent those functions as graphs. So suddenly you have these graphs connected in the control flow. So graph of graphs, so to say. And so if you do that, then suddenly solving your data flow problems just becomes a graph reachability problem. And so that's actually what we used. So there's one more important idea in that paper, which is summary edges. And summary edges means if you've already explored something, if you already know that if I go into this function and X is tainted, then the return value is tainted, then let's just create a summary edge of that. Then we don't have to compute that again. And that is really how you make taint analysis scale at all. And so our idea was, hey, let's just represent the entire code as call sites. Call sites and methods that are called. All of the operators. There is no plus or plus minus or some shift operator or something. None of that exists anymore. All we have is function calls, and we describe the semantics of these function calls using summary edges. Yeah, that's what we call the semantic code property graph. I'm going to hurry a little bit here now. And essentially it means all of the semantics of built-in operators are represented by these summary edges. All of the semantics of external libraries, including calls into native code, are modeled that way. And then finally, anything that you've already analyzed in that code base, you don't have to analyze again because we encoded semantic. And that's something really important if you want to scale this to all libraries, all frameworks out there. All right, so Marco will now tell you more about how to actually create all of, how to actually store all of these patterns in some way in this database so that you don't end up with just ad hoc queries, having 10 of them and then asking yourself, do we already cover this case? And so Marco, go ahead.
So right now we will present what we did to store all the knowledge base that we did. So basically we created our own language that looks like a firewall configuration. So the syntax is really basic. So it's basic to parse, to use and to save. So it's really simple. Everyone would say probably why you invented a new language, but don't worry, it's really easy. It's just few statements, and it's not a Turing complete language. So it's not like a complete new programming language. And the idea is to store all the summary edges as Fabian described. So all the semantics of all the functions. In this case, with the functional approach, everything is a function, so also operators and stuff. And also some rules about important input and outputs about programs and libraries, which in these ages people don't write code directly from scratch, but they use a lot of libraries, so we also need the semantics for all the libraries. So in the next slide I will show an example about how we write the semantics. So yeah, so this basically how it works, this machine. So we have all the knowledge base that it contains the semantics, the transformation, input, output, and flow description, and also some kind of customer related rules. So also the customer can write his own different rules, and this will be written in our syntax. And then of course the code property graph that synthesizes all the code as Fabian described before. And then both of the input goes into the full automat machine, and out of this full automat machine the output will be a security profile that we call like that because it's like the summary of everything that it's important about the code. So everything that it's toxic about the code. So here is like the basic example of how to define a semantic. So as described before, the functional approach, also operations like additions and shift and whatever is a function. So in this case, you can see the definition of a semantic of the addition. So you will see that the result of an addition is tainted both from the both operands. So from the first parameter and the second parameter, if you think as a functional approach. So in this case, in our syntax, it will be written like that. So in the red, you see the first parameter as a source. So the minus s means source, and the minus d is the destination. So we basically say that the first parameter will taint the return value during this operation, and also in the second line, you will see that also the second parameter will taint the return value of this operation. So both of the operand of this operation will end up in the result of this operation. So in this slide you will see something that it's a little bit more complicated. So that's like a library call. As you can see, there are more definitions needed. So basically you have a semantics that define in the first line you see from the parameter to the instance, because in this example is from Java, so object-oriented code, and you have the concept of instance. So in the first line you can see the parameter as a source will taint the instance itself. And as you can see from the last line, there is something that it's not really direct to think, that it's a mapping from the instance to the instance itself. And if you really think about it makes sense, because in the append operation also what is already inside the instance will matters in the instance after the operation. So both are needed, and what it's in the second and third line, it's also important in this case, because Java, for doing like better syntactic sugar, during the append operation they return the instance value, so you can concat a lot of append operations. So in this case also the instance will end up in the return value. So we need the same mapping from the parameter to the return value, as you can see from the third line of code, and also from the parameter to the instance itself. So that's just for the semantics. So right now we will go into detail about how to find important flows, so what it really matters, like finding vulnerabilities. So this is a really stupid code about Java. As you can see, there is like a get input stream that could be from a file in this case, and there are a lot of operations like reading from that buffer, creating a string buffer, and then at the end, after also some interprocedural call, it will end up in the read value function, that in this case is something important because in Java I do some kind of deserialization, which is one of the most important class of bugs in Java. So how we can try to find this, we can try to model these kind of vulnerabilities so the machine will find it automatically. So we basically define our source, and we can choose our tag name. In this case is a file. We choose like the full name and which part of the method it's actually the starting point from the source. So in this case, the return value, so the input stream object itself will be the starting point for the data flow operation. And of course, we also need to define our sink. So we can define in the same way you specify the full name, and also you specify what part of the method is actually what is important for the data flow. So in this case, what it's really should be controlled for data flow is the first parameter. So we specify the first parameter as the sink. And we also give us like a fancy name, deserializer, so it can be used in the results. But what's really important for vulnerabilities is not really to know if there is a flow from file or deserializer, but what is mostly important is the question, is something in the middle that is blocking this kind of data flow, some kind of escaping, some kind of encryption or whatever relate to this kind of flow. So yeah, it basically makes sense also to define this kind of transformation during the data flow. So how we can do that? We basically created also a statement to specify transformations. So transformations are functions called in the middle of the data flow. And in this case, we define an escape function, which also we define as a full name of the method, and also what enter, in this case is the sink as a parameter, and the return value is what is come out of this transformation operation. And on the last line you can see we attach some kind of tags that are really useful for data flow tracking, because sometimes you also want to remove this tagging during the data flow tracking. If you think about encryption and decryption, it's also important to think about the inverse operation. So at the end, the description of finding this class of vulnerability will be something like that. So defining the input as a source, the transformation, and the sink. Of course, you can specify multiple of them, and it's what is our knowledge base is based. So we have a lot of sink and sources, and also a lot of mappings that define the semantics of all the operations. So basically you define source, sink, escaping, and what is really important here is the definition of flow description. So as I said, a vulnerability is only important if you, in this case, it doesn't pass through the transformer, so if there is no transformation involved to the deserializer. So in this case we specify our flow as file not escaped. So during the data flow it shouldn't be passing through this transformer, and the data should end up in deserializer. So this flow will only be reported if these rules matches. So at the end you can see something like that. So basically, as I said, we will have multiple of this knowledge base, so a lot of policy definition, and which basically model a lot of different bugs, a lot of different data leaks and whatever is important to report. And then all of this will end up in our machine, and the results will be the security profile, as I said, so always toxic about the code. And this security profile is like a summary of all we found out about this. So as you can see in the information flow, you have a flow from a password to file, and there is some kind of transformation, which is MD5. So probably in this case MD5 is not the best. So right now we will have Niko that will show you some demos. So it's really working, our stuff. So welcome Niko to the stage.
Yeah, almost the whole team on stage. So next year, Valerio, if you get invited again, you if you get invited again, you will do demos too. Alright, so the first slide I wanted to make is that, I just want to state that we have only we are showing only a small subset of the features that we are currently have with the REPL. We are heavily developing features, and also at the very moment someone is sitting in our basement and working on our tickets. And also all the bugs we show we don't show them to just embarrass people. We love and support open source, and this is just something I wanted to have on a slide. Alright, so where we are, where is the REPL working, where at the Toolchain are we at the moment? And we are not in the vollautomat. We are here with the fingertips at the CPG, at the graph. So directly querying the graph. While we do this, while I'm showing this in some minutes or in some slides and demoing this, you don't need to use the REPL. We have, we have tools. We have the Java to CPG, CPG to SP tool. If you have a decent code base and you have a knowledge base and you have decent policy rules, you don't have to use the REPL. You can just say, create the CPG and get the security profile out of the CPG with our regular command line tools. Alright, back to the REPL again. If you aren't familiar with REPL, REPL means read, evaluate, print, loop. It's like, you know it from Python, it's like a prompt. And our REPL comes with several features. We have type checking, so also tab completion, read line support. We can pipe to other processes, so you don't have to, you're not jailed into our tooling. You can process the data with your favorite whatsoever, maybe pipe into Elasticsearch if you're happy with it. You can also extend it, you don't need to interact with it, you can just start scripts from the command line also. Yeah. Alright, so to query the graph, we introduced a language named Code Property Graph Language CPGQL. It's actually not a real language, it's not something you need to learn like the policy or I don't know, SQL, Rust or whatsoever. It doesn't take much time at all. Just a few minutes and you're in there. And what it offers here straight from the command line the information, all the information you need initially from an application, like namespaces, classes, methods, locals, members, method returns, whatsoever. Everything you want. You can use regex. Sure, you can trigger. You can find out about data flows, and if you want, you can also load policies on the fly. So the first project I want to show is a demo project we introduced for ourselves. It's just to train our tools, to work with our tools, and it is based on customer code. It's maybe artificial, but we have seen worse actually. So let's let's do this. Oh no, this is the demo stuff. All right, I already created a CPG with our from our jar. There's a Spring Boot jar. Spring Boot itself create a startable jar which you can execute from the command line. And you don't need a Tomcat whatsoever in it. And I'm jump right in. I'm loading the CPG as into the REPL, and I'm ready to query the application internals like namespaces. Here you can see name completion, and there you go. You see the name, all the namespaces which are packages in this case. And you can go down to classes, methods, and so on and so on. And as I said, you can use the regex. Let's see, what do we have? let's do another example. Actually, I'm starting with methods in most of the cases and go for the full name. You can match the exact full name or just a part full name. And I go with request. This is something you want to probably have initially, you're looking for initially if you're analyzing a binary or a tool. And you immediately get error messages, so you don't fire a query and get errors half of an hour later. But it should, you see, I had a typo. All right. So, and now we see all the methods including somewhere, including request somewhere, like web request. Yeah, you get it. Request attributes, which is maybe not that interesting. And I told you we can trigger data flows. We can figure out about reason about data flows in this through the REPL. And therefore I'm using a request as data flow object. So every method that contains request in the name and has parameters, I use the parameters as data flow object as a source, and we want to start our data flow tracking from there on. And let's say we are using read object, which is our really this is a general method which is really interesting during a pen test, so as a sink. And we defined our source, our sink. We say reachable by, and there you go. So we found several flows, and one of them is, as an example, do post login. And we see a parameter is coming in, which is named auth, and you can see the line number, which is actually matching. Yeah, it gets decoded from it gets base 64 decoded. Then it gets assigned whatsoever, and ends up in the end in a read object. So just with the two queries, or just with the three queries, three commands, you can reason about this method and what it eventually does, what could happen there. Yeah. Yeah. Okay, this is actually built on a customer code we saw. So let's go back to the slides. So this was a basic demo with artificial code, but we continue. Yeah, we have the demo fail slide, but the demo didn't fail. So you saw data flow tracking from source to sink. You saw some filtering, you saw syntax, how you can filter for regex, and then you maybe ask, how can I have more complex queries? Maybe I want to have a method name, maybe I want to have all the parameters of a method warn, which is called by a method in which the parameter in which the method get header is called with this very parameter x custom header. So it might be interesting for you, okay, is there a function where you have get header in it, and is there a logging whatsoever in it, and maybe you can find out, okay, they're reading the header, they're logging it, and custom header can be in this case a token or something else, which we also saw in customer code. Alright, so the next demo is Commons.io, which is maybe known. It's a very thin layer of file wrapper, and it has a, we call it parameter injection in it, although it is widely used and known. Let's see. Yeah, And here I'm also loading the CPG straight to a REPL. Yeah. And in this case, we are searching for the exec parameter method. What? Ah, yeah, got it. So, and we found a method. And also, there's also another feature of the REPL. You can go up. You can search for callers, and we find a caller. If you find a caller, but this time we are using, let's see, Unix, right? And so on and so on. So you get the principle. So you can interactively get information from the code. Sometimes we have also methods which are interesting but have no caller. You can easily reason about that and find out if they have a caller or not. But yeah, as you guessed, there's also a source matching to the sink. Well, it takes a few seconds. So we see we have parameter in free space KB, which is a string named path, and it eventually ends up in exec. So this is something this is something that would interest me as a pen tester or analyst or yeah, as a developer or whatsoever. And eventually, yeah, this is a short overview of the flow, but you saw the flow. And yeah, what we can do with this flow is we can inject parameters. You cannot manage to execute actually code or inject code, but you can manage to, I don't know, just pretend a different disk size, which can lead to denial of service. So, and as we said, it is a minor finding, yet a good example for data flow tracking. So we found the flow interactively on the REPL and doing some queries, but maybe you don't want to query or do this every time for every new jar, every new binary you get. You want to have this information stored, persisted somewhere else in the policy, and this is how it would look like. It's also pretty straightforward. Yeah. But Marco already talked about the policy. Right, next demo is OpenXava. OpenXava is a Java framework for rapid development. It has over 400 downloads a week. It's hard to find active Java CMS or frameworks that are used, and you can it's almost Java is dying in the as a CMS platform. Whatever. OpenXava comes with an invoice demo, and this demo has a CSV injection. Often CSV injection, people say, yeah, okay, I don't care about CSV injection, but CSV injection often pops up. And what it says is you can insert formulas that are interpreted by Excel or LibreOffice, and as soon as someone exports data from the page and opens this exported data with LibreOffice or Excel, code gets executed, or you can alter the sheets. Right, so we demoed this. Please, yeah, you can see this. I'm starting the server here. So as you can see, I added a parameter, a payload, according to the CVE I showed from 2018. And I saved the invoice. Right, that's enough for here. We say generate Excel. We export it. Move this to the side. This to the side. And as you see, this is my etc pass video. So even though I don't yes, first some demo phase slides. Whoop. My code. Wait. Yeah, so I'm loading OpenSava again. And we don't have that much time left, so I'm skipping the search process for this. Just using the sink and source. Right. So it also takes some time. Meanwhile, I'm showing another XSS in OpenSava. Yeah, there it is. And as you can see, we found out that there is a request coming in to GET request, and going straight through this method to CSV. Table data gets the table model. The data from the table model gets pulled and appended to a string. So it's just going through a table, and it eventually gets written out to the customer as file, to the user as file. Yeah, and here again we see the append annotation, which should not be whatever. Right. Time is getting again. Okay, we have demo fail slides. Okay, there's another XXS in OpenSava. Unfortunately. But I'm not going to demo them now. Just as a, I'm speeding up. Demo fail slides. Yeah, and this is one flow how you can, which helped us to find the the XSS triggered by the import. Yeah, we have some other vulns we found, but we cannot cover now. This is Crafter CMS, also XSS, and OpenCam. This is a stored XSS. There's actually more, but we don't have that much time left. Yeah, so this was the demo block. And maybe someone is asking, yeah, where's the cloud? Where's the cloud? So we are a startup, where's the cloud? And we do have a cloud. And it's hidden behind the screenshots. This is our UI. So if you want to have your files analyzed and have fancy GUIs, we can do that. Just ask us. And also inside the GUI you can see the data flows. Yeah. Finally, what's coming next? Yeah, we keep working on features. We keep working on other languages. So Java is just the beginning, and we have other languages in the pipeline. Yeah, also improving policies, and eventually maybe be able to rent the REPL, sell the REPL, I don't know. Maybe Fabs can sell something about this. Yeah, thanks.
If anybody has a question.
Do you wanna? What?
Hi. So one little question regarding, for instance, Java being a typed language, and do you actually have to care about the types that much? Because I could imagine, like for the plus operator, if you match it to a function, it's actually both string concatenation and the plus operation on numbers, where the one might have negative results on attaining, where the other one would have positive results. Do you actually have that already built in, or is that messing?
Especially this method is just mapped. We don't care about this, especially in the very moment. And yeah, since you cannot mess with memory that much in Java, we don't.
No, it's not about the memory. It's more about the typing. Does somewhere in your graphs, are you considering the types at all of the input data to some function to distinguish by type?
Yeah, just go for it.
So because the method might act differently depending on the type of the input.
Yeah, so you have all of the types in the graph. It's like a typed AST. You can use it, you don't have to. When it comes to annotations, you can write very generic ones that don't care about the type, and you can write caring about the type.
Thanks.
Thank you for the good presentation. Speaking about Java, in general, is it possible to find a path from source to sink if the application is using reflection for internal calls?
Yeah, we have some cases where we modeled that as well, but yeah, it is a lot more difficult with reflection. Maybe we can show you some of this offline, how we went about that, but yeah, reflection is definitely something tricky for static analysis always, and yeah.
Thank you.